Okay, I want to look at this problem, and I'm going to show you how I did it. Now, up on the boards, we saw the same answer. Everybody did it the same way that I did. But the reason I chose this was to show you something sort of unusual that I wanted to point out. When you look at this one, we know the pH is 11.5. We know the pKb is 4.74. So we start off by finding the pOH is 14 minus 11.5 is 2.50. Now remember when we first introduced buffers, what did I tell you to do when you're choosing your buffer system? Try and stay within 1 pH unit, right? And I said you can go outside of that, but some weird stuff happens, and that's what I wanted to show with this problem. So we are more than 1 pH unit away. So my requested pOH, 2.50, is equal to the pKb, 4.74, plus the log of ammonium or ammonia. So negative 2.24 is equal to the log of the ammonium to ammonia ratio. When I exponentiate, I get 0.0058 as my ratio. So I chose 0.0058 molar and 1 molar. Now I made the ammonium chloride salt 0.0058 moles per liter times 2 liters times the molar mass gives me 0.62 grams. That's not a lot of material, right? That's not very much. And then down here, I had, I want 1 molar times 2 liters times 17 grams per mole, 34 grams. So you see there that when we get outside of that range of 1 pH unit, we start to get either really small ratios, 0.0058, or we get really big ratios if you're more than 1 unit in the other direction. And so we want to stay away from that because it really affects capacity, which is what we're going to talk about next. So then we weigh this out, put it in a 2-liter volumetric flask, add water, mix, dilute to volume, and mix. And everyone did that correctly in their groups. So that's the thing that we want to be careful of, why that 1 pH unit is important. And I think it helps to see an example of that. Now, I've been alluding to buffer capacity for a while. And I want to talk about what happens when we add strong acid or a strong base to a buffer system. We're going to work with an acid buffer first. Oh, no, I guess we want to do one more thing here. Sorry. Using the Henderson-Hasselbalch equation to find the pH of a basic buffer. We learned to find the pH of a basic buffer using an ice chart. And we can also do it quick and dirty. We know that pOH is equal to pKb plus the log of the concentration of BH plus over the concentration of B. So we can just plug and chug like we did with the acid buffers. What's the pH of a buffer solution containing 0.1 molar ammonia and 0.050 molar ammonium chloride? Well, ammonium chloride is a salt, and it breaks down into its ions in solution, the ammonium ion and the chloride ion. What effect does the chloride ion have on pH, class? None, because it's the conjugate base of a strong acid. So if I have 0.050 molar ammonium chloride, I have 0.050 molar ammonium ion, which is my BH+. So my pOH is equal to my pKb for ammonia, 4.74, plus the log of my ammonium, 0.050 molar, divided by my ammonia concentration, 0.10 molar. So that's equal to 4.74 plus the log of 0.50. So the pOH is 4.74 plus a negative 0.30 is equal to 4.44. That's my POH. Now, the hardest part here, and where I see students make mistakes, is they stop. They're like, oh, I solved my equation. But remember, we're trying to find pH, not POH. So pH is pKw 14 minus 4.44 is equal to 9.56. And indeed, it is a basic pH, which is what we'd expect because we have a basic buffer. Yes? I hope I did this right. Okay, because 0.10 is ammonia, this is our base, and 0.050 ammonium, this is our conjugate acid of the weak base. This is our BH plus, and this is our B. And BH plus goes on the top. Okay? Remember, when we started equilibrium, we always said products over reactants for our KAs. And so we're being consistent. We have the product on the top and then the reactant on the bottom. Okay.